This is the second part of my video recording, as I intend to make each video clip short, within 15 minutes. So I am now making the follow-up video clip for the second lecture last week. So as you can tell that from the distribution planning perspective, the main thing is to ensure the demand that can be satisfied in a technical and economic feasible way. So right now, as if you were a utility, you have to carefully plan this out so that one thing that you need is data, and load forecasting is very, very important to determine what are the needs and hopefully can serve the customer reliably in the future. That means that they also have to find out what is the existing distribution system configuration and design, the substation site selection, and possible expansion. So this means that instead of building an additional feeder from a location to a very long distance, sometimes it makes more sense to build a new substation site, because the power loss over time can be saved, and eventually it will be wiser to do that at the building a one new power distribution transformer at another site. This can be true especially for the region that is spanned largely, so that that's the reason why we have a transmission system, is because we transfer the power in long distance from one place to the other to minimize the loss. And that means that if you have reduced the voltage, then proportionally the current will be increased. And that means that if the current increase, the I square is going to hurt the profit of the utility, because the larger proportion of power loss will be distributed throughout the entire region. And so that's all the factors have to be carefully planned out before they do that. So of course that building a new substation site will require some capital that they have to carefully plan on in terms of the finance of the utility. So this is basically the flow chart about everything. As you can see that this is a typical ComSci 101 thing, the flow chart, but the main thing here is the data, which is the forecast. And the forecast is another challenging part of it, is because we don't have every metering point at every part of the network. So sometimes planning engineer have to be selectively pick out the location or load type and do thoroughly the statistical analysis and find out where, and then based on the best knowledge to find out the information. I will talk a little bit about that in the next chapter of this book, because this is what we do in terms of predicting how much the power loss will be, and then determine the voltage profile for a particular feeder depending on the shape that we want to determine. So those are the language I just mentioned, that whether or not they want to build a new substation or expand the present network, which means that they are going to add a new feeder from existing power substation. And so this is an iterative evaluation, maybe monthly by monthly or even annually, and see what is the best way to do to optimally operate the distribution feeder. So soon enough that we're going to touch on the load characteristics chapter, which will be chapter 2 of the textbook. The tricky part of the study is that there is a diversity and uncertainty of the load, which largely is not meters. I introduced a keyword called AMI, Advanced Metering Infrastructure / sometimes people call it automated meter reading. So they mean the same thing, except that there are some trivial difference in terms of control capability. But there's also a term called demand response. So those are the things that refer to the ability of the consumer, which is us, to be able to do some sort of control. Hopefully that will help us to optimally operate our household consumption in an efficient manner. So load characteristic is a very challenging matter to utility, because they have to find out the diversity of the meters, because they don't know for every out of the 1,000 customers within a feeder, they could be very different from each other. But as I said, the metering point is limited, and then there's also uncertainty they have to take care of. and the widespread and large number, as I said, there's a number thousand of customers. They have to sort of cluster or categorize them into different load types so that they can do the planning study better. At any kind of optimization study, there's always a constraint, and as you know, this is no exception in this case, that we have to carefully find out what is the planning constraint. So as enumerated on this page, we have a service continuity, what's the maximum allowable peak load profile drop to a certain customer, the voltage dip due to motor starting, and then service reliability, power losses, power quality, etc. Those are the constraints that the planning engineer have to carefully consider. And of course, that some of the data we might not even have it, because there's no meeting point that can acquire with a higher resolution. So a lot of time that the utility have to do their best shot to predict the not just the data, but also the possible constraint after talking with some of their critical customer, that to find out what are the ability that they can help them to serve the power reliably. So as you know, that to plan out the distribution system expansion and all sort of thing, they are always subject to as I highlight here, judgment and their experience, as well as the new technology. So so a lot of time it may make sense to do it in a proper way, but because of other constraint and their experience in the past, that what they find out, they can do things a little bit different. But we are changing the way how we operate the system in the future, so there are some technology that we can actually leverage, and hopefully that will help to enhance the load characteristic of the study, so that the utility will understand the system much better, so that they can plan this ahead of time, and then everyone is happy when they have the power. Particularly, this is a very challenging job for a developed country like in America, that power outage is really the crucial subject. So people are talking about what would be the SID and CHID, the measures, CHID, those are the reliability matrix, which I will talk about that later on the semester. These are the one to measure the system performance and the customer duration of power outage. And a lot of time that sometimes they get the data inferred from the feeder head of the system when the breaker trip or not trip, and then there's a whole timestamp appear in the SCADA system. So those are the things that they will use to determine the reliability of the distribution network. And of course, that there's no hard rule and say this should be done in this way or that way. It's all dependent upon how the system has been operated in the past, and of course, judgment and experience does matter at most. So for the next 2 pages, I'm just going to briefly truly about what the equipment characteristic and the economic of skill and all that. So this page is also dealing with the loss and radial operation, and how much the reserve power capacity would have. So those are the major concern of the utility. What are the things that they need to operate? All the material that I presented for the first 2 lectures are actually sort of the information extract from these 2 references. I don't require you to buy multiple books for this class, but at least minimally the Kersting textbook, especially the 3rd edition, is something that you need to own one, just to avoid inconvenience throughout the semester, because sometimes I assign the homework based on the numbering system from the textbook, and equation figures, they all changes from edition to edition. So this will get you confused if you buy a cheaper older version. So think about this, and moreover, you can actually sell the book once you use it. So if you don't like to keep that book after use it, you can always sell it and get the money back in a certain proportion. Of course, if you get lucky, you might get 100% back, but that's how this textbook is being invested. But I strongly recommend to keep these books for the rest of your semester, even sometimes it will be useful handbook for you to use it when you are at work. Say you work for utility that in the distribution planning division, this might be a good book for you to have in your shelf. So to sum up what we have talked about for the first two lectures, these are the important keywords, a summary. So you have the primary, secondary network, radial, unbalanced, and of course I can say that it's a loop or ring configuration, mesh network, feeder, lateral, and then power transformer, usually referring to the injection source of power, the only source that we have mostly today that the power that we get the power from the utility. And this is a distribution transformer referred to the load. If you want to analyze a distribution system purely within a primary network, a distribution transformer is actually a load. And you will experience something that we might have to deal with the distribution transformer modeling later on, because sometimes we might be considering that there is a power loss in power transformer. So modeling carefully about how the primary network of distribution model would actually help us to determine how much the power loss for each distribution transformer. So this is a important subject that we will be going through. Hopefully in the end that we will see the bigger picture, that how it affects the load flow analysis, which will be based upon the backward forward sweeping technique. And then distribution substation, and then remote control switch. So you have a normally open switch, NO, stand for NO. Sometimes you call it tight switch, or NC switch, normally closed switches. And then you have fuse, and of course that we've been talking about unidirectional flow of power from power distribution substation all the way to the loads. So those are the pictures I draw during the class, and I don't intend to redraw the whole thing, but you get the whole picture is that they are multiple elements of the distribution system. A feeder could consist of thousands of customers. Many switches could include non-remote controllable switches. As I mentioned, they are server protection devices. Recloser is actually the one that plays far away from the substation, because sometimes the circuit breaker might not be able to see the fault occur far away. So placing strategically a recloser between a distribution feeder may be helpful to pinpoint the fault location as a result. And you can see that recloser will close here instead of here, so you don't have to experience a complete feeder de-energization. Instead, you might have some partial outage, and hopefully that might the distribution management system will be able to recommend some switching action to isolate the fault, as well as to resume the power to the healthy power segment of the distribution grid from other source. So those are the things that I mentioned, and then this is the major difference between distribution system and transmission system. So you can see there's a balanced radial, loop / parallel, or ring, you call it the same way, but mostly if you want in the distribution operation, when they do it in a loop or parallel or ring, that could mean in an emergency condition. They don't do it often under normal operating condition. And on the other extreme, the transmission system that have been characterized in a different attribute with balance and mesh. So as you can see, one of the reasons that why you need this course to handle distribution system characteristic is that there's a very different characteristic in distribution system that we have to address. Particularly if you learn from 4221 and 4222, those courses will teach you how to run a load flow analysis in per phase basics, and then the construction of Y matrix is actually built based on the mesh topology of the network. So specific handling of this load flow inverse of the Y matrix may not be as tricky as the three-phase more inflated version of the Y. So we are going to explore the different technique to run a load flow analysis. And in the transmission system, I'm sure you heard about the Newton-Raphson, Gauss-Seidel, fast decarbonate technique. Those are the technique that used to handle the Y matrix, whereas we are going to just simply deal with this in the distribution system just on the 3x3 side of Z impedance matrix. Of course, this might be, we might be going through this graph transverse of the backward forward between a distribution feeder, which in graph theory we refer it as a spanning tree. So you have a root node and then the children nodes between the network, and the root node is referred to feeder head, and then the child node is actually the loads of the feeder. So that's the difference between these two network. And finally, the major objective of this course is to determine, after having all this detailed modeling and all that, what is of interest is we want to find out how much the power losses would be, because in transmission system we sort of ignore the R, the resistor, because it's the reactance is much more significantly larger than the R. It's not the case in distribution system. And then there is also the voltage regulation within a feeder. So having known what would be the voltage profile is very, very important in distribution engineering. So with that, I think this will conclude lecture 2. And if you have any question about what we have, just feel free to send me. And this is the last picture I sent out. I think most of you have got it. Is that this is the picture that show one line diagram, single phase circuit, and then when we were given the 12.747 kV, it means the line to line voltage or line voltage. So in the circuit schematic diagram, you have to divide by square root of 3, because what you need here is a phase voltage or line to neutral voltage. So, and I'm trying to relate this line voltage at VLL to line to neutral. So basically you have to divide it by square root of 3, and then there's a 30-degree difference depending upon the sequence that you need to do. And to find out the receiving voltage magnitude, basically you have to do this as a voltage divider by summing out all the impedance information for denominator value, and then the nominator value will be simply 3 plus J4, and then multiply by the source voltage. That will give you the VR voltage magnitude with angle. Thank you.